Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. So find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, let's continue with one of my favorite science readings on this podcast, Astronomy for Young Folks by Isabel Martin Lewis, A.M., connected with the Nautical Almanac Office of the U.S. Naval Observatory. First published in 1922 by Duffield and Company, New York. Let's pick up right where we left off at the beginning of chapter 26. Let's begin. Chapter 26. Keeping Track of the Moon. Of all celestial objects, the nearest and most familiar is our satellite, the Moon. Yet the mistakes and blunders that otherwise intelligent persons frequently make when they refer to the various aspects of the Moon are quite unbelievable. Who has not read in classics or in popular fiction of crescent moons riding high in midnight skies, of full moons rising above western cliffs or setting beyond eastern lakes? Who has not seen the moon drawn in impossible positions, with horns pointing toward the horizon, or a twinkling star shining through an apparently transparent moon? Careful observation of the moon in all its various phases and at different seasons is the best method to be used in acquiring a knowledge of the elementary facts regarding the motion of the moon through the heavens from day to day. But that requires that one be up often after midnight and in the early hours preceding dawn, and so it is that we feel so hazy in regard to what happens to the moon after it has passed the full. A few fundamental rules can be easily acquired, however, and these will enable us to locate the moon in the right quarter of the heavens at any time of the day or night, when we know its phase and the approximate position of the sun at the same instant, and thus we may avoid some of the most obvious blunders that are made in dealing with the general aspect of the moon at any given time. As can be verified by direct observation, the moon is always moving continually eastward. Since it makes a complete revolution around the earth from new moon back to new moon again in a little less than 30 days, it passes over about 12 degrees a day, 360 degrees divided by 30, on the average, or 1/2 a degree an hour, which is about the angular extent of its own diameter. Therefore, every hour the moon moves eastward a distance equal to its own diameter. This is of course only approximate, as the moon moves more rapidly in some parts of its orbit than in others. In addition to its real eastward motion, the moon shares the apparent daily westward motion of all celestial objects, which is due to the daily rotation of the earth on its axis in the opposite direction. That is, the moon, as well as the sun, stars, and planets, rises in the east and sets in the west daily. On account of its continuous eastward motion, however, the moon rises later every night, on the average about 50 minutes, though the amount of this daily retardation of moonrise varies from less than half an hour to considerably over an hour at different seasons of the year and in different latitudes. In the course of a month, then, the moon has risen at all hours of the day and night and set at all hours of the day and night. It might seem unnecessary to emphasize the fact that the moon always rises in the east, were it not that the astronomer occasionally meets the man who insists that he has at times seen the moon rise in the west. To be sure, the new crescent moon first becomes visible above the western horizon shortly after sunset, though it rises in the east the morning of the same day shortly after sunrise. As is also true of the sun, the exact point on the horizon where the moon rises or sets varies from day to day and from season to season. In 1 month, the moon passes over very nearly the same path through the heavens that the sun does in 1 year, for the moon's path is inclined only 5 degrees to the ecliptic or apparent path of the sun through the heavens. It can never pass more than 28½ degrees, 23½ plus 5 degrees south of the celestial equator, nor more than 28½ degrees north of it. It has a slightly greater range in altitude than the sun, therefore. North of 28½ degrees north latitude, it always crosses the meridian south of the zenith, and below 28½ degrees south latitude, it crosses the meridian north of the zenith. In tropical regions, the moon sometimes passes north of the zenith, sometimes south, or again directly through the zenith. Since the full moon is always diametrically opposite to the sun, it passes over nearly the same part of the heavens that the sun did 6 months before. In winter, then, when the sun is south of the equator, the moon rides high at night north of the equator, and vice versa. In summer, when the sun is north of the equator, the full moon rides low south of the equator. In winter, then, we have more hours of moonlight than we have in summer. This may be of no great advantage in mid-latitudes, but we may imagine what a boon it is to the inhabitants of the Arctic and Antarctic regions to have the friendly moon above the horizon during the long winter months when the sun is never seen for days at a time. At time of new moon, the moon lies directly between us and the sun, but ordinarily passes just to the north or south of the sun, since its orbit is inclined 5 degrees to the ecliptic or plane of the Earth's orbit. If the moon's path lay exactly in the ecliptic, we would have an eclipse of the sun every month at new moon, and an eclipse of the moon 2 weeks later at full moon. Now the moon crosses the ecliptic twice a month, the points of crossing being called the nodes of its orbit. But only twice a year is the moon nearly enough in line with the sun at the time it crosses to cause eclipses. Every year, then, there are 2 eclipse seasons, separated by intervals of 6 months, when the moon is in line with the sun at or close to the point where it crosses the ecliptic. Then and only then can solar and lunar eclipses occur. The solar eclipses, of course, will occur when the moon is new, that is, when the moon passes directly between the earth and the sun and throws its shadow over the earth, and the lunar eclipses 2 weeks later, when the earth passes between the sun and moon and throws its shadow over the face of the moon. Probably there is no astronomical subject that has been more generally misunderstood than that of solar and lunar eclipses. It is well to remember that solar eclipses can only occur at time of new moon, and lunar eclipses only at the time of full moon. And at the time of eclipses, whether lunar or solar, the moon is at or near its nodes, the points where its orbit crosses the ecliptic. There are always at least 2 solar eclipses every year, and there may be as many as 5. There are years when there are no lunar eclipses, though ordinarily both solar and lunar eclipses occur every year, some partial, others total. The moon shines only by reflected sunlight. It is of itself a solid, dark body, with its day surface intensely hot and its night surface intensely cold, a world of extreme temperatures. At new moon, all of the night side of the moon is turned towards us. At full moon, all of the day side. At other phases, we see part of the day side and part of the night side, and the illuminated side of the moon is always the side that is towards the sun. Failure to observe this simple rule leads to many grievous blunders in depicting the moon. At the time of new moon, the moon, moving continually eastward, passes north or south of the sun from west to east, except when it passes directly in front of the sun, causing eclipses. A day or so later, the waxing crescent moon, or the new moon, as it is popularly called, becomes visible low in the west immediately after sunset. The moon is now east of the sun, and will remain east of the sun until the time of full moon. During the period from new moon to full moon, it will therefore rise after the sun and set after the sun. The waxing crescent moon will not be visible in the morning hours, because inasmuch as it rises after the sun, it is lost to view in the sun's brilliant rays. Nevertheless, it follows the sun across the sky and becomes visible in the west as soon as the sun has disappeared below the western horizon. The thin illuminated crescent has its horns or cusps turned away from the point where the sun has set. The horns of the crescent can never point toward the horizon, since the illuminated side of the moon is always turned toward the sun, whether the sun is above or below our horizon. As hour by hour and day by day, the moon draws farther eastward and increases its angular distance from the sun, more and more of the illuminated side becomes visible. The crescent increases in width and area, and the moon appears higher in the western sky each night at sunset. Usually, about 7 and a fraction days after the date of new moon, the moon completes the first quarter of its revolution around the earth. The period from one phase to the next is variable and irregular, being sometimes less than 7 days, and at other times more than 8 days, since the moon does not move at a uniform rate in different parts of its orbit. When the moon has completed the first quarter of a revolution, it is 90 degrees east of the sun and presents the phase known as half moon, since half of the surface that is turned toward the earth is illuminated and half is in darkness. It is said to be at the first quarter. The illuminated half is of course the western half, because the sun is to the west of the moon. The half moon is near the meridian at sunset and sets near midnight. Up to the first quarter, then, the moon is a crescent in the western sky during the first part of the night and should never be represented as east of the meridian or near the meridian at midnight. After the moon has passed the first quarter and before it is full, more than half of the side turned toward the earth is illuminated, and it is in the gibbous phase. It is still the western limb that is fully illuminated. The moon is now east of the meridian at sunset, and it crosses the meridian before midnight and sets before sunrise. All who are abroad during the first half of the night find this phase of the moon more favorable to them than the gibbous phase following full moon. The moon, now being above the horizon at sunset, is visible continuously from sunset to midnight, but sets sometime during the second half of the night, while the full moon shines throughout the night, rising in the east at sunset and setting in the west at sunrise. When the moon is full, it is 180 degrees east or west of the sun, and so both its eastern and western limbs are perfectly illuminated. After the full, the moon goes through its phases in reverse order, being first gibbous, then a half moon once more, and lastly a waning crescent. It is now west instead of east of the sun, and so it is the eastern limb that is fully illuminated by the sun. Being west of the sun, it will now rise before the sun and set before the sun, the interval decreasing each day as the moon draws in toward the sun once more. The gibbous phase preceding full moon is favorable to all abroad before midnight, but the gibbous phase following full moon is more favorable to those who are abroad after midnight, for from full moon to last quarter, the moon is below the horizon at sunset, and of course is rising later and later each night, while at sunrise it is still above the horizon, appearing each day higher and higher above the western horizon at sunrise as it approaches the third or last quarter. When it has reached this point, it is once more a half moon, though now it is the eastern half instead of the western half of the disk that is fully illuminated. The moon is 90 degrees west of the sun at third quarter, and from this phase to the phase of new moon, it is a crescent once more, but now a waning instead of a waxing crescent. It appears east of the meridian before sunrise, and as the crescent grows thinner, it draws nearer and nearer to the eastern horizon and the rising sun. As with the waxing crescent moon, the horns are turned away from the horizon. The waning crescent moon is always to be looked for east of the meridian and to be associated with the rising sun, while the waxing crescent moon is to be looked for west of the meridian and associated with the setting sun. Neither the waxing nor the waning crescent moon will be visible during the midnight hours. As the waning crescent moon grows thinner and draws in closer to the sun each successive night, its time of rising precedes that of the sun by an ever-decreasing interval, until finally the crescent disappears from view in the eastern sky. The next day we see no crescent either in the eastern or western skies. The moon is once more in conjunction with the sun and new. One revolution of the moon about the earth with respect to the sun has been completed, and a day or so later, we may look for a new crescent moon in the western sky after sunset. Chapter 27: The Motions of the Heavenly Bodies. About 320 years ago, Giordano Bruno was burned at the stake for his audacity in believing in the existence of other worlds. A few decades later, the famous astronomer Galileo was forced to publicly recant his belief that the Earth moved. Yet the truth could not long be suppressed by such means, and since those dark days, man's advance in knowledge has been so rapid that it seems to us today, in this wonderful age of scientific discovery, almost inconceivable that man ever believed that the Earth, a tiny planet of a vast solar system, was the hub of the universe, the fixed and immovable center about which revolved all the heavenly bodies. Very reluctantly, however, and with bitter feeling, but in the light of overwhelming evidence, man finally gave up his long-cherished idea of terrestrial importance, and when finally forced to move his fixed center of the universe, he moved it only so far as the comparatively nearby sun. This center he then regarded as fixed in space, and also held to his belief that the stars, set in an imaginary celestial sphere, were immovable in space as well, and all at the same distance from the sun. So scarcely 200 years ago, we find that the astronomer Bradley was endeavoring to measure this common distance of the fixed stars. Though he failed in his attempt, he made the important discovery that the observed positions of the stars are not their true positions, owing to the fact that the velocity of light is not infinite, but takes a definite finite interval of time to travel a given distance. As a result, the stars always appear displaced in the direction of the Earth's motion around the sun, the amount of displacement depending upon the velocity of the Earth in its orbit and the velocity of light. This aberration of light, as it is called, furnished additional proof that the Earth revolves around the sun, and was one more nail driven into the coffin of the old Ptolemaic theory that the Earth was the center of the universe. Bradley also discovered that the positions of the stars were affected by the wobbling of the Earth's axis, called its nutation. Although in the days of Bradley, neither the methods of observation nor the instruments were sufficiently accurate to show the minute shifts in the position of the stars that reveal the individual motions of the stars and the distances of those nearest to us. Yet the discovery of the two large displacements in the positions of all the stars, due to the aberration of light and the nodding of the Earth's axis, were of the greatest value, for they were a necessary step in the direction of the precise measurements of modern times. It is only through measurements of the greatest refinement and accuracy that it is possible to detect the motions and distances of the stars and to discover the wonderful truths about the nature and structure of the universe that they are revealing to us today. After unsuccessful attempts extending over several centuries, the distance of one of the nearest stars, the faint 61 Cygni, as it is catalogued, was finally determined by the astronomer Bessel in the year 1838. This star is about 10 light-years distant from the Earth, which places it about 630,000 times farther away from us than the Sun. That is, we would have to travel 630,000 times the distance from the Earth to the Sun to reach this very close stellar neighbor, 61 Cygni. The nearest of all the stars, Alpha Centauri, is over 270,000 times the distance from the Earth to the Sun. It is therefore little wonder that the early astronomers believed that the stars were fixed in space, since even the nearest is so far away that viewed from opposite points in the Earth's orbit, its apparent change in position due to our actual change in position of 186 million miles amounts to only 1.5 seconds of arc. Two stars separated by 160 times this angular distance might possibly be glimpsed as two distinct stars by a person with good eyesight, though to most of us they would appear as one star. Upon the measurement of such minute angles depended a knowledge of the distances of the nearest stars. It is to Sir William Herschel that we owe the discovery, more than 100 years ago, of the motion of the sun through the universe. From the consideration of a long series of observations of the positions of the stars, this famous astronomer discovered that the stars in the direction of the constellation Hercules were separated by much greater angular distances than the stars diametrically opposite in the heavens. In other words, the stars were spreading apart in one portion of the heavens and crowding together in the opposite direction. And he rightly interpreted this to mean that the sun was moving in the direction of the constellation of Hercules. It was not until the spectroscope was applied to the study of the heavens in the latter part of the 19th century that the amount of this motion of the sun was found to be about 12.5 miles per second, or 4 times the distance from the Earth to the sun in a year. It is to Sir William Herschel that we owe also the discovery of binary systems of stars, in which two stars swing around a point between them, called their center of gravity. Our first conception of the immensity and grandeur of the universe dates from the time of the older Herschel only a century or so ago. The mysterious nebulae and star clusters were then discovered. The wonders of the Milky Way were explored, and a new planet and satellites in our own solar system were discovered. It was found that the sun and the stars, as well as the planets, were in motion. Neither sun nor earth could be regarded any longer as a fixed point in the universe. With the application of the spectroscope to the study of the heavens toward the end of the 19th century, the key to a treasure house of knowledge was placed in the hands of the astronomers of modern times. And as a result, we are now learning more in a few decades about the wonders and mysteries of the heavens than was granted to man to learn in centuries of earlier endeavor. Yet it is the feeling of the astronomer of today that he is only standing on the threshold of knowledge, and that the greatest of all discoveries, that of the nature of matter and of time and space, is yet to be made. It is the spectroscope that tells us so many wonderful facts about the motions of the stars, nebulae, and star clusters. It tells us also practically all we know about the physical condition of our own sun and of the other suns of the universe, their temperature and age, and the peculiarities of their atmospheres. Some of the most important astronomical discoveries that have been made in the past few years have to do with the distribution and velocities of the heavenly bodies as revealed by the spectroscope. It has been found, with the aid of the spectroscope, that the most slowly moving of all stars are the extremely hot bluish Orion stars, with an average velocity of 8 miles per second, while the most rapidly moving stars are the deep red stars with an average velocity of 21 miles per second. And there is in all cases a relationship existing between the color or spectrum of a star and its velocity. The reason for this connection between the two still remains undiscovered. The spectroscope has also told us some astonishing facts in recent years about the velocities of the spiral nebulae. It is now known that these mysterious objects are moving with the tremendous average velocity of 480 miles per second, which exceeds the average velocity of the stars full 25-fold. They possess, moreover, internal motions of rotation that are almost as high as their velocities through space. It is now generally believed that spiral nebulae are far distant objects of enormous size and mass, exterior to our own system of stars and similar to it in form. In place of the universe of the fixed stars and the immovable sun or earth of a few centuries ago, we find that modern astronomical discovery is substituting a universe of inconceivable grandeur and immensity in a state of ceaseless flux and change. Our Earth, an atom spinning about on its axis and revolving rapidly around a huge sun that is equal in volume to more than 1,000,000 Earths, is carried onward with this sun through a vast universe of suns. Only an average-sized star among several 100,000,000 other stars is this huge sun of ours, moving with its planet family through the regions of the Milky Way, where are to be found not only moving clusters and groups of stars speeding along their way in obedience to the laws of motion of the system to which they belong, but also strangely formed nebulae covering vast stretches of space, whirling and seething internally and shining with mysterious light, and still other stretches of dark obscuring matter shutting off the rays of suns beyond. The extent and form of this enormous system of stars and nebulae, and the laws that govern the motions of its individual members, are among the problems that the astronomers of today are attempting to solve. On both sides of these regions of the Milky Way, wherein lies our own solar system, lie other vast systems, such as the globular star clusters, composed of thousands, possibly hundreds of thousands of suns. The Magellanic Clouds, which resemble detached portions of the Milky Way, and probably the much-discussed spiral nebulae, possible island universes similar to our own. We have come far in the past 300 years from the conception of an immovable Earth at the center of the universe to this awe-inspiring conception of the universe that we have today, which is based upon modern astronomical discoveries. Whatever may be discovered in the future in regard to the form and extent of the universe, the idea of a fixed and immovable center, either within the solar system or among the stars beyond, has gone from the minds of men at last. Not more than a generation ago, a survival of the old idea of a fixed center was seen in the belief that Alcyone in the Pleiades was a central sun, about which all the stars revolved. It is now well known that the Pleiades form a moving star cluster. Alcyone is therefore drifting slowly onward through the universe, and the idea of a fixed and immovable center to which man may anchor his ideas is drifting away also. There are, it is true, local centers of systems, such for instance as the Sun occupies in the solar system, or some group of stars may occupy in the stellar system to which our Sun belongs. Yet, as a whole, these systems move on, and their centers with them. There is no evidence today that any absolutely immovable point exists in the heavens. No celestial object has been found to be without the attribute of motion, not only motion onward through the universe, but also rotational motion about an axis of the body. The planets rotate on their axes as well as revolve about the Sun, and the Sun also turns on its axis as it moves onward through space. This rotational motion is also found in the nebulae and star clusters, as well as in the stars and planets. No object in the heavens is known to be without it. Even the slowly drifting Orion Nebula possesses a rapid internal velocity of rotation. There is no such thing as a body absolutely at rest in the universe. Chapter 28. The Evolution of the Stars, from Red Giants to Red Dwarfs. The most casual of stargazers is aware that the stars differ one from another in color and in brightness. There are red stars, yellow stars, white stars, and bluish-white stars. There are the brilliant stars of first magnitude, such as Vega, Capella, and Antares. And there are, on the other hand, stars so faint that they can barely be glimpsed with the most powerful telescopes. In general, the most brilliant stars are the nearest, and the faintest stars are the most distant. But there are many exceptions to the rule, since there are stars that appear faint even when comparatively near, because they are small and shine with a feeble light. Such a star is the faint sixth magnitude star 61 Cygni, one of the nearest of all the stars. Again, there are stars in far distant clusters, visible only in powerful telescopes, that in actual brightness exceed our own Sun several thousand times, and in volume several million times. A star the size of the Sun would be invisible in the most powerful telescope in existence if it were at the distance of many stars in the Milky Way or globular star clusters. Stars differ in color because they differ in temperature. We are all aware of the fact that a piece of iron, when heated, first glows a deep red, then appears yellowish in color, and finally attains to white heat. It is the same among the stars. The red stars are the coolest of all the stars, and the bluish-white stars are the hottest of all the stars, while intermediate between them in temperature come the yellow and the white stars. Now, as the biologist and the geologist see in this world of ours signs of evolution, or gradual development and change from the simple to the more complex forms, and of growth and decay, so the astronomer sees among the stars signs of a continuous progressive development from one type of star to another. Stars share in the general evolution that is the law of the universe, and are born, reach the height of their development, decline to old age, and die. Within the past few years, important astronomical discoveries have been made that show the true order of this evolution of the stars. It was believed not so long ago that the blue-white helium stars, the type B stars the astronomers called them, or the Orion stars, since there are so many stars of this type in the constellation of Orion, were not only the hottest, but also the youngest of the stars, and that they represented the first stage in the development of a star from a primitive gaseous nebula, such as the Great Orion Nebula. It is now known that these brilliant hot helium stars represent the peak of development of the most massive of all the stars, and not the first stages in the development. A star, it is now known, comes into existence as a giant reddish star of enormous size, and of a density only about 1,000th that of the Earth's atmosphere at sea level. It is inconceivably tenuous or rare, and its temperature is comparatively low, about 3,000 degrees centigrade or less. It is not evolved from the luminous gaseous nebulae, because red stars are never found associated with the gaseous nebulae, as are the blue-white stars. The origin of these red giant stars is uncertain, but it is possible that they may be gradually evolved in some manner from the dark clouds of obscuring matter or dark nebulae that exist so abundantly in the heavens. In the next stage of its development, the deep red giant star increases in temperature as it contracts under the action of gravitation, and its color gradually changes from red to yellow. Its density increases slightly, and its volume decreases. It is now a yellow giant star. As the evolution progresses in the course of ages, the star continues to contract. Its temperature increases greatly, as does also its density, and it continues to decrease in volume. It is now a brilliant white star, a hydrogen star, so called because its spectrum is chiefly characterized by the lines of hydrogen. As the star contracts under the gravitation of its parts and increases in temperature and density, there comes more and more into play an important factor that has a great effect upon its future development. This is light pressure or radiation pressure, which acts in opposition to gravity and exerts a strong outward pressure upon matter within the depths of the star, tending to push it outward from the center where the temperature is greatest and the light is most intense. It is a most interesting fact that if the mass of a star, that is, the quantity of matter that it contains, exceeds a certain value, the pressure of light or radiation within it overbalances the gravitational attraction that draws matter towards its center, and the star disintegrates or ceases to exist as a star. This accounts for the fact that the stars differ very little among themselves in the quantity of matter that they contain, that is, in their masses, though they may differ enormously in size. Stars that exceed a certain mass will become unstable, and this may account for the association of luminous nebulae with the hottest of all stars, the nebulae possibly being puffed off from the surfaces of these stars under the action of radiation pressure. After a star has reached the height of its development as a bluish-white helium star with a temperature of something like 10,000 degrees centigrade and a density about 1/10 that of the Sun, it begins to lose heat and to cool gradually, though it continues to contract and increase in density. It is now on the descending scale of evolution, and is to be counted among the dwarfs instead of the giants. A brilliant blue-white helium or Orion star is about 100 times more luminous than the Sun, and its diameter is about 10 times that of the Sun. Our own Sun, we find, is on the descending scale of stellar evolution. It is a yellow dwarf star of temperature about 6,000 degrees centigrade and density 1 1/4 that of water, which is probably about as great a density as is attained by any star, since even the non-luminous planets Jupiter and Saturn have lower densities than the Sun. The last stage in the development of a star is represented by the dwarf red star of high density and low temperature. The diameter of the dwarf red star probably averages about 500,000 miles, and its temperature is 3,000 degrees centigrade or less. After this, we have the extinct stars, similar possibly to our planet Jupiter, though considerably larger, with a dense gaseous atmosphere and a certain degree of internal heat. We have traced the evolution of a star from a red giant to a red dwarf, through the intermediate stages from yellow giant to a giant helium star with increasing temperature, and thence to yellow dwarf and red dwarf as the temperature decreases. Only the most massive stars pass through this entire chain of evolution. Stars of small mass never attain to the splendor of brilliant blue-white helium stars, but begin to decrease in temperature and brightness before this stage is reached. The time required for the evolution of a star from red giant to red dwarf is not known, but it must be very great. The age of the Earth, which is probably equal to that of the solar system, is estimated as something like 1,000 million years. It is probable that the average life of a star far exceeds this limit. And with that speculative statement, which is both true and not at all true, I think we'll end this evening's reading from Astronomy for Young Folks. I think I love this book so much because I do know a lot about astronomy, and it's fascinating to see how that science has evolved over time. I hope you enjoyed it as well. If you'd like to read this work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.